Welcome to the Deep Dive. If you're looking for the shortcut to being truly well-informed on the cutting edge of science, you are definitely in the right place. Today, we are taking a real molecular trip into what feels like the future of tissue repair. We're zeroing in on an engineered peptide it's completely captivated regenerative research circles. It's called PTD-DBM. Our focus today is really understanding a pretty fundamental biological mechanism. This peptide, PTD-DBM, it's making huge waves in studies around, hair regrowth and skin regeneration. But its genius isn't really about adding external factors like growth factors. The core concept here is precision biological engineering. It works by removing a natural internal inhibitor. So it's not like hitting the accelerator, it's more like releasing the brakes on the body's own built-in regenerative potential. We're going to make sure you walk away understanding the precise molecular structure, the mechanism of action, how it actually flips the switch, the really quite stunning preclinical findings, and, importantly, the immense practical hurdles researchers are tackling to bring the science forward.
Absolutely. And look, before we dive deep into the amino acid sequences and the cellular pathways, we really must establish the essential context here, based on the source material we've reviewed. Everything we discussed today, it's based strictly on preclinical findings, detailed research reports, studies conducted in very controlled laboratory settings or animal models. We need to be absolutely crystal clear on this. The molecules discussed, and that includes PTD-DBM, are currently subject to research restrictions. They are explicitly not intended for human consumption or any kind of therapeutic use. Okay, our entire discussion is confined strictly within the boundaries of scientific investigation, looking into potential future applications. That's key.
That is absolutely the essential groundwork for this discussion. Thank you. Now, okay, let's get into the molecule itself. PTD-DBM, that name is quite the mouthful, isn't it? But it sort of describes exactly what the molecule is designed to do.
It really does. PTD-DBM stands for Protein Transduction Domain Disheveled Binding Motif. And it's quite an elegant piece of biological engineering. It's comprised of 24 amino acids, which gives it a molecular mass of approximately 3.08 kilodaltons, or kDa. What's immediately important for you to grasp, I think, is that this wasn't just some accidental discovery. It was specifically designed as a fusion peptide. Think of it like two different functional machines welded together for a single, highly targeted mission. And this structure, it serves as a superb model for how future targeted peptide design might work.
Okay, right. Let's unpack that two-part design then, because this really seems to be where the brilliance of its function shines through. It sounds like an elegant solution to a massive biological challenge.
Right.
How do you target a regenerative signal deep inside the cell?
Exactly. PTD-DBM has to perform two very specific jobs, and each part is engineered to handle one of them.
So part one is the PTD, the protein transduction domain. You mentioned it's kind of like the VIP pass. It's designed to get the whole molecule across the cell membrane, past the inner security gate, so to speak. How does it actually manage that? It sounds difficult.
Well, the mechanism is based on charge and structure. This segment, the PTD part, contains a repeating sequence of 8 arginine residues. Arginine is positively charged. This creates a highly charged sort of polyarginine structure. Now, the cell membrane itself has negative charges on its surface.
Okay. Positive attracts negative.
Precisely. The positively charged PTD section acts almost like a chemical grappling hook. This specific sequence is actually a recognized cell-penetrating peptide, or CTP. What that means is once the overall molecule successfully navigates the outer physical barrier of the tissue, like the stratum corneum in skin, which is tough, this polyarginine structure efficiently drags the relatively large 3.08 kilodA molecule straight through the internal cell membrane and into the cytoplasm.
Into the cytoplasm, where the action needs to happen.
Exactly, where the machinery is.
So the PTD is this highly specialized delivery system. That's incredibly clever engineering. Okay, now we move to part two. The DBM, the disheveled binding motif. This is the functional core, you said, the piece that actually flips the switch inside. What precisely is its target?
Right. The DBM is meticulously structured. Its job is to target a very specific protein interaction, and this interaction sits right within a crucial signaling network called the Wnt-catenin pathway. To really understand why PTD-DBM is potentially so powerful, we have to appreciate the significance of this particular network. Wnt-catenin.
Wnt-catenin. Okay, it sounds highly technical, but the source materials we looked at, they really elevate it far beyond just another molecular name. They describe it as a critical master program, or even a green light for tissue creation. Why is Wnt signaling so fundamental for regeneration?
Because it essentially is the ultimate genetic instruction set for building and rebuilding tissues. Want signaling controls really fundamental processes. Cell proliferation, that's the sheer growth of cells. Cell differentiation, meaning cells becoming specialized types, and overall tissue regeneration. Think about hair follicles, for instance. One is the signal that basically kicks the follicle out of its resting phase and pushes it into the growth phase, the anagen phase. It tells the stem cells, okay, time to build a hair.
And without that Wnt activation.
The process just stalls. The follicle stays dormant or, worse, shrinks.
Okay, and this is where the body naturally introduces some brakes, right? It doesn't want runaway growth all the time, so it installs an inhibitory mechanism. What is this biological brake that PTD-DBM is designed to release?
That brake is a protein named CXXC5. It's a well-recognized Want antagonist, basically a negative regulator. In the body's normal state, when it's not actively regenerating or growing rapidly, CXXC5 is active. Its job is to keep that potent Want signal quiet, ensuring cells don't just proliferate or differentiate unnecessarily. It maintains homeostasis.
Right, controlled growth. So how does CXXC5 manage to shut down such a, well, complex master program like Want? What's the specific molecular step it interferes with?
It does this by binding to another key protein called disheveled, or DVL for short. You can think of DVL as a critical scaffolding protein or maybe a signaling hub inside the cell. Normally, when the Want signal arrives at the cell surface receptor, DVL organizes the next steps downstream. These steps allow the core driver of the pathway, a molecule called patenin, to escape being destroyed.
Okay.
But when CXXC5 is attached to DVL, it effectively handcuffs that signaling hub. This attachment prevents the accumulation of free active patenin inside the cell. And because BAM is normally degraded very rapidly when Want is inactive, if it can't accumulate, the growth genes down in the nucleus remain silent. The build instruction never gets sent.
Okay, so CXXC5 blocks DVL, DVL can't stabilize BTL, and the whole regenerative process stays dormant. That makes sense. So here's where PTD-DBM becomes potentially revolutionary. How does this 24-amino acid molecule successfully disarm such a tightly controlled system?
PTD-DBM operates as a highly specific, high-affinity decoy molecule. This is the key. The DBM segment of the peptide, the second part, has been specifically engineered to perfectly mimic the exact segment of the CXXC5 protein that normally attaches to DVL.
It's a mimic.
Yes. So when PTD-DBM is introduced and successfully penetrates the cell, thanks to the PTD part, it essentially floods the system. It competitively binds to that DVL signaling hub. It literally occupies the docking site where CXXC5 would normally attach. It muscles CXXC5 out of the way.
So it's not actually attacking or destroying CXXC5 directly, it's just winning the parking spot on DVL.
Precisely. That's a great analogy. It's an incredibly targeted form of competitive inhibition. And this seemingly simple competitive interference has a profound and almost immediate downstream effect. Once CXXC5 is effectively blocked from binding to DVL, the entire Want signaling cascade is basically set free. The inhibition is lifted.
And what happens then?
This causes the central player, buccatenin, to become stabilized. It stops being constantly targeted for degradation, so it starts to accumulate rapidly inside the cytoplasm. And when enough buccatenin accumulates, it then translocates. It moves into the cell nucleus.
And once patenin gets into the nucleus, that's when the switch is well and truly flipped.
Absolutely. Inside the nucleus, buccatenin acts as a co-transcription factor. It binds to specific DNA sequences and effectively turns on the target genes. These are the specific genetic instructions required for cell growth, for proliferation, for differentiation, all the things needed for regeneration. So PTD-DBM enables the body's own regenerative system simply by removing that inhibitory brake, allowing the natural, powerful growth script to execute. And that distinction, removing an inhibitor versus adding an outside growth factor, that's what makes this mechanism so incredibly compelling to researchers.
It really is a phenomenal example of precision biology in action. Okay, now that we've got a handle on the molecular mechanics, let's see this mechanism applied. Starting with the area that is perhaps most clinically challenging for many people, regenerating hair and tackling pattern baldness.
Yes, the potential here focuses squarely on androgenetic alopecia common pattern baldness, which is, as you say, a condition notorious for its resistance to truly permanent solutions.
Can you give us the quick context again on the molecular basis of this condition? Why does hair loss happen in pattern baldness?
Well, androgenetic alopecia is really defined by hair follicle miniaturization. What happens is the follicle itself progressively shrinks over time. In its growth cycle, the anagen phase becomes shorter and shorter until eventually the hair produced is almost invisible, like peach fuzz, or the follicle just stops producing hair altogether. This whole detrimental process is tightly linked to reduced activity of that want pathway we just discussed, and it's often triggered by the effects of DHT, dihydrotestosterone, a potent androgen.
DHT.
DHT basically suppresses the proliferation signals within key cells of the follicle, like the dermal papilla cells. Less want activity means more shrinkage.
Okay, so we have a hormonal signal, DHT, telling the follicle to shrink and eventually die off, and this process involves shutting down or suppressing one activity. So where does PTD-DBM fit into that picture? How could it help?
PTD-DBM's potential role here is to essentially bypass or counteract the effects of that androgenic suppression caused by DHT. The idea is, even when DHT is present and trying to suppress Wnt, by physically blocking CXXC5 with the PTD-DBM decoy, the peptide forces the Wnt signal to reactivate anyway.
Ah, it overrides the DHT signal in a way.
It aims to restore that critical green light necessary for cell proliferation and differentiation within the follicle structure, potentially overriding the signals that are pushing towards miniaturization. The sources suggest that by removing that CXXC5 brake, you allow the Wnt pathway to establish the required momentum for sustained growth, potentially even despite the presence of those miniaturizing hormones.
That's a really powerful theoretical outcome. What did the preclinical findings actually demonstrate? Did it work in the animal models?
The results reported were highly encouraging, yes. Topical application of PTD-DBM showed a significant boost in hair regrowth in standard depilated mouse models. They saw a faster onset of anagen, more robust growth. However, the most significant and frankly surprising finding was evidence of something called wound-induced hair follicle neogenesis.
Okay, let's really underscore that term, neogenesis, because we're not just talking about thickening up existing miniaturized hairs, which is basically the aim of most current hair loss therapies like minoxidil or finasteride. We're talking about creating a fundamentally new biological structure, aren't we?
Precisely. Neogenesis means the formation of completely new hair follicles in areas where none previously existed or where they had been lost. This mechanism was observed specifically in wounded or previously bald areas of skin that were treated with PTD-DBM, especially when combined with other factors. This capability, true structural regeneration, making something brand new, is the major step change that really distinguishes PTD-DBM from existing preservation or enhancement treatments. It implies the peptide might be powerful enough to reprogram the local tissue microenvironment, pushing it back towards an almost embryonic-like regenerative state.
Wow. Creating new follicles. That's the holy grail for hair loss research, isn't it?
It really is. It suggests potential beyond just stopping loss. It hints at actual reversal.
Okay, so if the peptide is releasing the main brake, researchers are always looking for ways to kind of, maximize that signal, get the best possible effect. Did they find synergistic combinations? Did other things help boost the regenerative outcome even further?
They absolutely did. And this really highlights the complexity of triggering true tissue regeneration. It's very rarely just a single switch solution. It's more like tuning an orchestra. They found that the results were markedly improved when PTD-DBM was paired with other molecules that also, maybe more generally, enhance Wnt signaling activity.
Interesting. What were these auxiliary boosters, and how do they differ fundamentally from PTD-DBM's very targeted action on CXXC5?
Well, the first notable combination involved valproic acid, or VPA. Now, VPA is a well-known compound used for other medical purposes, but in this context, it acts primarily as a histone deacetylase inhibitor, an HDAC. VPA's action is much more generalized compared to PTD-DBM. By inhibiting HDAC enzymes, it promotes what's called an open chromatin structure in the cell nucleus.
Meaning the DNA itself is more physically accessible for reading.
Exactly. It basically makes the DNA sequences, including the ones that are targeted by Wnt signaling, more generally accessible to the transcription factors that need to bind to them. So, while PTD-DBM is very specifically blocking CXXC5 to release abunkinin, the key Wnt driver VPA is sort of preparing the nuclear environment. It's gently amplifying the potential response across the board by making those target genes easier to read and activate.
So one is a precision key, PTD-DBM, and the other, VPA, is maybe like loosening the entire lock mechanism slightly.
That's a pretty good analogy, yes. PTD-DBM provides the specific signal, while VPA enhances the cell's overall readiness to respond to that signal.
That dual action is fascinating. Highly specific release plus general amplification. The sources also suggested, though, that a physical element was really key to achieving the absolute optimal results.
Yes, absolutely critical. The optimal strategy, the one that yielded the best follicular regeneration and neogenesis outcomes in the studies,
Hmm.
involved the physical preparation of the tissue using microneedling alongside the application of both PTD-DBM and VPA. The role of microneedling here is crucial, and it's actually multifaceted. It's not just about getting the stuff in.
Ah, so it's not just about delivery then, it does more.
Not entirely, no. Microneedling serves at least two key roles. First, yes, delivery. It physically breaches that formidable stratum corneum barrier. It creates direct microchannels for the relatively large PTD-DBM molecule and the VPA to actually access the dermal layers where the follicle stem cells reside.
Okay, that makes sense. Get it past the gate.
Right. But second, the microinjury itself initiates a localized inflammatory response and a wound healing cascade. This controlled injury is actually a known precursor signal for activating dormant stem cells and jump-starting regenerative pathways, including WIND.
So you're kind of waking the tissue up with the injury?
Exactly. You're setting the stage with a controlled microinjury signal, then you're amplifying the gene readability with VPA, and then most powerfully, you're removing the central biological brake on regeneration with PTD-DBM. It's really a beautifully coordinated attack on biological stasis designed to push the tissue firmly towards regeneration.
That combination strategy, physical prep, general amplifier, specific brake release, really showcases the kind of multidisciplinary thinking needed in this cutting-edge research.
Okay, let's shift focus now to the second major application area. How does PTD-DBM influence skin healing and maybe crucially the quality of skin repair?
Well, the great thing is the underlying molecular principles remain identical because skin repair, just like hair follicle cycling, relies very heavily on that same white signaling pathway.
Right. What specifically does Wnt do in a healing wound? Why is it so important there? Wnt is like the conductor of the wound healing orchestra. It's critical for keratinocyte proliferation. That's the process that allows the skin surface to reform and close the gap, known as reepithelialization. It also stimulates fibroblast activity. Fibroblasts are the cells that generate the structural foundation of the dermis, the collagen, and elastin scaffolding. And critically, Wnt signaling regulates the synthesis of quality collagen and other extracellular matrix components needed for strong functional tissue.
Okay, so if Wnt is vital for good healing, then presumably if CXXC5 is present and active, we see the brake being applied to healing as well, slowing things down.
Absolutely. The research clearly shows that if CXXC5 is overexpressed in a wound, if that brake is applied too strongly or for too long, the wound healing process is severely impaired. Wound closure slows right down, and the quality of the repair suffers dramatically. You often end up with disorganized or insufficient collagen deposition, which leads to weaker tissue or more prominent scarring.
And conversely, if you block CXXC5.
By contrast, when CXXC5 is experimentally blocked or inhibited, healing accelerates significantly.
Okay, tell us about the evidence from the animal models, specifically looking at wound repair. What improvements did they actually observe beyond simply wounds closing faster?
So yes, the treatment with PTD-DBM did lead to wounds closing measurably faster. But as you hinted, the quality of the repair was arguably the headline finding. Researchers observed significantly higher collagen content in the healed tissue, and critically, they saw much better tissue organization within that newly formed matrix compared to controls.
Why does tissue organization matter so much when we talk about wound healing? Isn't faster closure the main goal?
Faster closure is good, but the quality determines the long-term outcome. Disorganized, haphazardly laid down collagen is essentially the definition of scar tissue. It's often weak, inflexible, and looks different from normal skin. When the tissue organizes correctly during healing, with collagen fibers aligned properly and a structure that resembles the native unwounded skin, the functional and aesthetic outcome is far, far superior. The evidence from the PTD-DBM study suggests that it promotes this better organization, potentially reducing the formation of that poor quality fibrotic scar tissue.
Okay, so what's happening at the cellular level that drive this improved organization and quality? What are the fibroblasts doing differently?
Well, in fibroblasts, those primary structural cells, PTD-DBM treatment led to a demonstrable increase in facnin stabilization, just as we discussed before. And this led to a corresponding surge in the production of collagen, particularly types I and III, which are crucial for skin strength. Furthermore, this enhanced fibroblast activity resulted in stronger collagen matrix contraction. That's the process that physically pulls the wound edges together efficiently. And it also accelerated the reepithelialization from the keratinocytes. Essentially, the fibroblasts are being instructed by the reactivated Wnt signal to lay down a stronger, more organized, and more efficient scaffold for repair.
So it's not just a quick patch job. It's really optimizing the body's own genetic blueprint for a more complete and functional reconstruction.
That's precisely the key takeaway, I think. PTD-DBM serves as a prime example, a model, really, for a regenerative medicine strategy that focuses on activating the body's intrinsic healing and building mechanisms. We are not adding external materials like a scaffold or excessive growth factors. We are simply allowing the natural, high-quality repair program, which is already encoded in our genes, to run uninhibited by removing a specific break.
Given the fundamental nature of the WNT pathway controlling basic building processes, does the research hint at potential applications beyond just hair and skin? You mentioned bone earlier.
Yes, the sources strongly suggest that this is a foundational biological principle. Since WNT signaling is also known to be a major player in regulating bone density and the activity of osteoblasts, those are the cells that actually build new bone. Research is actively exploring PTD-DBM-inspired compounds in that area. Early indications suggest that lifting WNT inhibition, perhaps by targeting CXXE5 or similar regulators in bone tissue, could potentially enhance bone density and osteogenesis. This opens up some really exciting research avenues for conditions like osteoporosis, or perhaps even for accelerating the healing of complex bone fractures.
That is a massive potential scope from hair to skin to bone. But we absolutely must return to the practical reality here. The huge jump from promising lab findings to any kind of real-world efficacy hinges entirely on one major bottleneck: delivery. This peptide, PTD-DBM, has to get through the tissue barrier and into the target cells to work. How big is this delivery hurdle in practice?
It is without doubt the single largest practical hurdle. It's really the elephant in the room for almost all larger therapeutic peptides, especially fusion peptides like this one.
Okay, let's just revisit the specs quickly. 24 amino acids, a molecular weight of about 3.08 kilodaltons, kDa. Why does that size make something like simple topical application, like in a cream, so incredibly difficult?
It comes down to the basic principle of passive bioavailability across the skin. For molecules to passively diffuse across the stratum corneum, that tough, outermost layer of dead skin cells, the skin's primary barrier, they typically need to be very small. The general rule of thumb is below 500 Daltons, FEPS-DTB. PTD-DBM is over $3,000, so it's about 6 times larger than that ideal passive diffusion limit.
Way too big to just sneak through.
Way too big. Plus, its structure makes it relatively water-soluble, which also hinders passage through the lipid-rich stratum corneum. This size and solubility profile make oral administration completely impractical. It would just be degraded in the stomach. And it renders simple passive absorption through intact skin highly ineffective. Its use, therefore, must be targeted and localized, and usually requires some form of assistance.
Right. And you mentioned the PTD segment, the cell-penetrating part, ensures entry into the cell once it's past the skin barrier.
Yeah.
But getting it across that initial barrier, the stratum corneum, remains the primary challenge. What kind of assistance is absolutely necessary to bridge that gap effectively?
The peptide benefits tremendously. In fact, it often requires physical or mechanical delivery methods that temporarily compromise or bypass that stratum corneum barrier. As we discussed earlier in the context of hair regeneration, researchers rely heavily on techniques like microneedling. This creates microscopic, transient channels directly into the epidermis and potentially the upper dermis.
Allowing direct access.
Exactly. Fractional laser treatments are another method explored. These use focused laser energy to create controlled microthermal zones or channels, again, creating pores for delivery. These kinds of methods are pretty much essential in the research setting to ensure the peptide actually reaches the target cell layers efficiently and in sufficient concentration. Without them, the vast majority of the applied peptide would likely just sit on the surface and degrade.
Okay, so let's say we manage to solve the physical barrier problem with microneedling or lasers. We then immediately face the chemical barrier. Stability. You can't just put a delicate, precisely structured biological molecule like a 24 amino acid peptide into a standard consumer cream or serum and expect it to remain intact and functional for weeks or months on a shelf, can you?
Absolutely not. That's the other major challenge. PTD-DBM, like the vast majority of peptides, is highly vulnerable chemically. It faces proteolytic degradation, being chopped up by enzymes called proteases that are ubiquitous on the skin surface and even within formulation ingredients. It's vulnerable to oxidation from exposure to light and air. And it can suffer from general chemical instability within standard liquid or emulsion vehicles, especially those containing water.
And if that 24 amino acid sequence gets broken or even slightly altered?
The whole thing fails. Particularly the DBM segment needs its precise structure to maintain that high affinity binding to DVL. If the sequence is compromised, it loses its ability to act as an effective decoy, and the entire mechanism of action is lost. Function gone.
So what are the cutting-edge methods researchers are actually employing to try and enhance the stability and preserve the sequence integrity of PTD-DBM? This seems like where the formulation science really has to meet the molecular engineering head-on.
It's a huge area of research. They're working on several sophisticated chemical and physical modification strategies. On the chemical side, they look at modifying the peptide molecule itself. One interesting approach is substituting the natural L-amino acids with their mirror image counterparts, D-amino acids, at key positions or even for the whole sequence.
D-amino acids, how does that help?
Well, the proteolytic enzymes found in biology are typically specific for L-amino acids, the naturally occurring forms. They often don't recognize or can't effectively cleave peptide bonds involving D-amino acids. So incorporating D-amino acids can make the peptide versions far more resistant to enzymatic breakdown, significantly extending their biological half-life and potential efficacy in a real-world biological environment.
That's brilliant. Essentially hiding the peptide in plain sight from the degrading enzymes. Clever. What about physical protection strategies? Encapsulation.
Yes, advanced encapsulation techniques are critical. Probably the most common approach involves entrapping the peptide inside protective structures like liposomes. Liposomes are tiny spherical bubbles made of phospholipids similar to cell membranes. They can effectively shield the fragile peptide molecule inside from external stressors like enzymes, pH changes, and oxidation.
Like a tiny armored transport.
Pretty much. Researchers are also exploring more complex systems like multiple emulsions, for instance, water and oil in water, WOW emulsions, which can stabilize the water-soluble peptide in an interior aqueous phase, protected by surrounding oil and water layers. And for the absolute highest standard of purity and stability, especially in research or potential early clinical settings, many systems rely on providing the peptide in a lyophilized or freeze-dried powder form.
Freeze-dried, like astronaut food.
Exactly like that. Lyophilization removes almost all water, which is a key medium required for many degradation pathways. The stable powder then needs to be carefully reconstituted with a specific solvent or vehicle just before application. This ensures maximum sequence integrity right up until the moment of use, often packaged in single-use ampoules protected from light and oxygen.
Wow. This level of complexity really underscores why that regulatory disclaimer you gave at the beginning is so critically important. This isn't just mixing up a simple cream. Controlling delivery and stability at this level is definitely not trivial. And then, circling back slightly, there's the safety question again. If WANT signaling is such a potent master switch for growth and proliferation, how do researchers ensure they achieve only localized, time-limited activation without risking unintended side effects from overstimulation?
That is a crucial consideration. And it's all about dosage, localization, and control. WENT is powerful. If it's activated systemically throughout the body, or it's activated chronically for too long even in one tissue, it can potentially lead to aberrant signaling. This could theoretically cause issues like hyperplasia, which is uncontrolled tissue overgrowth, or possibly other unintended cellular changes. The risk profile needs careful evaluation. So the sources consistently emphasize that the research goal is strictly controlled, localized activation. You want just enough signaling for just long enough to prompt the target effect, like pushing a hair follicle into anagen or ensuring complete wound closure, and then the signal must dissipate naturally or be actively stopped. It's about precision in time and space.
Okay, so given the significant delivery and stability headaches associated with this relatively large PTD-DBM fusion peptide, are researchers actively looking for smaller, perhaps easier to handle alternatives that could achieve the same biological outcome, blocking CXXC5?
Absolutely. That's a major thrust in the field. The challenges with the peptide have directly driven the development of small molecule mimics. The sources specifically cite a compound named KY19382 as an example of this approach. This compound was designed through screening and optimization to specifically block that crucial CXXC5-DVL protein interface, but using a much smaller non-peptide chemical scaffold.
A small molecule inhibitor instead of a peptide decoy.
Exactly. Small molecules, generally speaking, offer several potential advantages. They are typically much easier and cheaper to synthesize in large quantities. They often possess inherently superior passive absorption properties simply because of their smaller size and potentially more favorable physicochemical properties. And crucially, they can potentially be formulated into more stable, conventional delivery systems like creams or solutions with much higher precision and longer shelf life compared to the large, fragile fusion peptide.
So that small molecule route might represent a more practical path towards eventual therapeutic translation.
It certainly represents a significant focus for future translational research, yes. It could potentially overcome many of the hurdles associated with the PTD-DBM peptide itself, while hopefully retaining the core therapeutic benefit of releasing the Wnt break.
Right. We've covered the intricate mechanism, the exciting potential applications in hair and skin, and the really immense practical and structural challenges. Now let's try to situate PTD-DBM within the broader landscape of cosmetic and research peptides that our listeners might already recognize or even use. It really feels like it belongs in a completely different class, doesn't it?
It absolutely does. PTD-DBM represents a fundamental shift in pharmacological strategy, I would say, compared to most of the established cosmetic peptides that people might know.
Okay, let's do a quick comparison.
Yeah.
Let's start with maybe the most famous cosmetic peptide, arginine, known for its Botox-like effects. What is its mechanism, and how does it differ?
Arginine, or acetyl hexapeptide 8 technically, is a highly functional peptide, typically a hexapeptide, so 6 amino acids. Its mechanism is focused entirely and solely on the neuromuscular junction where nerves talk to muscles. It works by modulating the snare complex proteins, specifically targeting one called SNF25. This protein is necessary for the release of neurotransmitters like acetylcholine that cause muscle contraction.
So it stops the muscle contracting.
It temporarily interferes with that neurotransmitter release process, leading to muscle relaxation. This results in the reduction of dynamic wrinkles, the ones formed by facial expressions. Crucially, arginine has absolutely no regenerative function. It doesn't interact with dermal matrix components like collagen, nor does it touch the Wnt pathways we've been discussing. It is purely cosmetic and anti-contraction. Different world entirely.
Okay, completely different mechanism. Now, contrast that with something like Matrixyl or its various forms like Matrixyl 3000 or Synthor 6. These are often hailed as the gold standard for structural support and anti-aging. How do they work?
Matrixyl peptides, and there are several iterations, are classified as signaling peptides, sometimes called matrikines. They are usually short fragments derived from naturally occurring structural proteins, often from collagen or elastin breakdown products. When applied to the skin, they act as a biological signal to fibroblasts, the skin's builder cells. They essentially trick the cell into thinking that the extracellular matrix has been damaged or degraded and needs replacement.
Like a false damage signal?
Kind of, yes. This stimulates the fibroblasts to boost their production of new collagen, various types, elastin, and hyaluronic acid. This helps improve skin structure, firmness, and texture over time. So while matrixyl peptides are excellent for anti-aging support and boosting matrix components, they're still focused on enhancing the production of existing structural elements. They aren't designed to initiate deep tissue regeneration in the same way PTD-DBM aims to, nor are they involved in complex processes like hair follicle neogenesis.
Right. Still promoting building, but not flipping a master regenerative switch. Okay, one more comparison. What about GHKQ, the copper tripeptide? It's renowned for its roles in healing and recovery.
GHKQ is another fascinating peptide, a tripeptide complexed with a copper ion. It's fantastic for promoting generalized skin health and wound healing. It promotes broad healing responses, functions as a potent antioxidant, helps remodel and renew the extracellular matrix, and the copper ion itself is essential for various enzymatic processes involved in tissue repair, like collagen synthesis and angiogenesis.
So quite multifunctional.
Very multifunctional, yes. However, its action is more akin to generalized support, coordination, and renewal of the skin environment. It does not possess the highly targeted specificity of PTD-DBM, which is engineered to block one specific inhibitory protein, CXXC5, in order to flip an internal regenerative master switch like Wnt-catenin. GHKQ is broader support. PTD-DBM is targeted release.
Okay, that clarifies it nicely. So if arginine is muscle relaxation, matrixyl is structural component signaling, and GHKQ is broad healing support and renewal. PTD-DBM's unique role is really what? Sum it up again.
PTD-DBM is the intrinsic biological switch activator. It's best categorized as a true regenerative peptide because its primary goal isn't just to enhance or support existing processes, but rather to reactivate the body's own deepest growth and repair programs by directly addressing a root cause of their inhibition, the CXXC5 break. This level of targeted manipulation of internal regulatory protein interactions really places it in a different league, conceptually, from most cosmetic peptides.
Yeah, it really does sound like a different paradigm.
Yeah.
Okay, shifting gears slightly, let's look at the science itself for a moment. For our listeners who are really keen to understand the rigor behind these kinds of groundbreaking findings, how do labs typically structure these complex regenerative studies involving compounds like PTD-DBM? The sources mentioned a kind of four-step framework. What are the core steps and metrics they focus on?
Right. The methodology needs to be extremely rigorous and highly focused on measurable objective outcomes, especially when you're claiming things like neogenesis. Generally, labs investigating these compounds follow a logical four-step framework. Step one is about establishing the receptive microenvironment. The tissue needs to be appropriately primed or challenged. As we discussed, this often involves creating controlled wounds, using specific depilation protocols to synchronize hair cycles in animal models, or employing techniques like microneedling. The point is to initiate the relevant local healing or cycling signals and, importantly, to break the skin barrier for delivery. This ensures the compound is being tested in a complex biologically active setting, not just on passive tissue.
Okay, prime the tissue. Step two then focuses on the product itself.
That's right, delivery and protection. Researchers must rigorously demonstrate that the PTD-DBM peptide, or its analog, is not only getting across the skin barrier effectively, but also that the chosen vehicle, whether it's a liposome, a special gel, a reconstituted lyophilized powder, is successfully preserving the integrity of that delicate 24 amino acid sequence long enough for it to reach the target cells and bind to DVL. This often involves detailed analytical chemistry, like HPLC analysis, both before application and sometimes recovered from the tissue, to confirm the peptide is intact and present.
Makes sense. Verify it gets there in one piece. Step three is about optimizing the biological activation.
Correct. This often involves exploring the combination strategy. Researchers will systematically test the inclusion of potential want cofactors or amplifiers, like the valproic acid VPA example we discussed. They need to quantify whether the combination therapy yields statistically significantly superior results compared to PTD-DBM used alone or VPA used alone. This helps confirm the synergistic nature of the regenerative cascade and identifies the most potent approach.
Right, finding the best recipe. And finally, step four, the proof is in the data. What measurable outcomes, what specific endpoints are they actually tracking to prove it works?
They track highly specific, quantifiable endpoints relevant to the application. For hair regeneration studies, this means meticulously tracking the anagen entry ratio, that's the percentage of hair follicles actively shifting from the resting telogen phase to the active growth anagen phase over time. They also measure changes in total hair density and sometimes hair shaft thickness using phototrichograms or histology.
Very precise measurements.
Very precise. For skin wound healing studies, they measure wound closure kinetics, literally, how fast the wound area shrinks over time. They perform detailed histological analysis of the healed tissue to assess collagen deposition, collagen fiber organization, and the overall quality of the tissue architecture compared to controls. They might measure markers of inflammation or re-epithelialization rates. And increasingly, they look directly at the molecular level within the cells, using techniques like Western blotting or immunofluorescence to specifically track the increase and, crucially, the nuclear translocation of betanin, confirming the target pathway was indeed activated. It's all about verifiable quantitative data points.
That's incredibly thorough. It gives you confidence in the findings when that level of rigor is applied. Okay, looking towards the future then, the promise of this kind of technology, manipulating regenerative switches, feels immense. Where do you realistically see the most likely application paths for PTD-DBM and its analogs actually moving forward, given the challenges?
Well, based on the current state of the research, and particularly the delivery challenges, I see the field likely moving in two clear directions, at least initially. The first and perhaps nearer-term track involves highly controlled, procedure-paired clinical approaches. What I mean by that is using PTD-DBM, or a highly optimized analog in a controlled clinical or dermatology setting, applied immediately following specific procedures. Think about deep scar revision treatments, complex non-healing wound care protocols in hospitals, or perhaps dedicated in-clinic hair restoration sessions, where mechanical delivery methods like microneedling, fractional laser, or maybe even localized injection are already being employed by a professional.
So piggybacking on existing procedures where delivery is managed.
Exactly. In that kind of controlled setting, the potentially higher cost and complexity of the peptide formulation and the need for assisted delivery become more justifiable because of the significant clinical need, e.g. severe scars, chronic wounds, and the fact that the delivery mechanism is part of the overall treatment protocol anyway.
Okay, that makes sense for specialized applications. What's the second track?
The second, and probably more impactful long-term track, is the continued evolution of the molecule itself. As we discussed, there will be intense focus on discovering and developing next-generation small molecule analogs. Compounds like the KY19382 example that successfully capture the essential CXXXC5 blocking functionality, but within a much more stable, deliverable, and formulation-friendly small molecule scaffold.
The search for the easier version.
Pretty much. The ultimate success, really the pinnacle of this line of research, would be to achieve reliable, potent, and localized regeneration that is predictable, stable, and critically proven safe enough for potentially broader dermatological or therapeutic use beyond just highly specialized procedures.
Predictable, localized regeneration. That truly is a goal worth chasing, isn't it? This has been a tremendously insightful deep dive into what feels like a genuinely revolutionary molecular mechanism. So just to quickly recap the core message for everyone listening, PTD-DBM is this cleverly targeted engineered fusion peptide. It acts as a highly specific molecular decoy. Its DBM segment competitively blocks the natural inhibitory protein, CXXC5, from binding to the crucial Wnt signaling hub, DVL. This action effectively releases the molecular brake on the fundamental Wnt-catenin master pathway. This in turn enables the body's own powerful repair and growth script to drive deep regeneration. We saw evidence for this potentially, including the formation of entirely new structures like hair follicles, that remarkable neogenesis, and also promoting faster, higher quality, potentially scar-reduced wound healing in the skin. The immense potential efficacy of flipping this biological switch is, however, currently entirely dependent on overcoming significant practical hurdles, primarily in delivery getting the large molecule where it needs to go, and also in formulation keeping it stable and active. This often requires mechanical assistance, like microneedling, and sophisticated chemical stabilization techniques.
Exactly. And that leads us perfectly, actually, to our final provocative thought for you, the listener, to take away from this deep dive. If PTD-DBM and the research into its analogs and mimics demonstrates that we can accurately and locally manipulate specific internal inhibitory proteins like CXXC5 to effectively turn on powerful regenerative processes, potentially even overriding damage or decline previously considered inevitable, like hormone-induced follicle shrinkage or the age-related degradation of tissue quality, then what other common biological limitations processes we currently view as just permanent aging or irreparable injury or unavoidable scarring could potentially be redefined in the future as fundamentally reversible simply by identifying and then precisely removing a newly discovered break specific to that process?
Wow, it really changes the entire perspective on biological damage and aging itself, doesn't it?
Yeah.
From something to manage to potentially something to reverse by finding the right switch. We strongly encourage you to continue exploring this emerging field of targeted fusion peptide design, small molecule mimics, and the incredible bioengineering involved in cellular delivery and pathway manipulation. It's definitely a space to watch. Thanks for joining us for the deep dive.